rational numbers and irrational numbers. Rational numbers and irrational numbers. So in rational numbers, what is rational numbers? A number, a real number or a number expressed, a number which is expressed in the form of p by q, where q does not equal to 0, where q does not equal to 0, those numbers we can call it as rational numbers. Those numbers we can call it as rational numbers. What are the examples of rational numbers? Here 1 by 2, 2 by 3, 1 by 4, 8 by 4, these all are etc. These all are examples of rational numbers. Examples of rational numbers. Next, coming to irrational numbers. Coming to irrational numbers, a number which is not expressed in the form of p by q, not expressed in the form of p by q, where q does not equal to 0, where q does not equal to 0, those numbers we can call it as irrational numbers. And one more thing, in irrational numbers, root of all the prime numbers, root of prime numbers are irrational numbers. Already we know prime numbers. What is mean by prime number? A number which have only one factor, which is have only one is a factor and itself. Means, for example, 2 is a prime. 2 is a prime number. What are the factors of 2? 2 and 1. What are the factors of 2? 2 and 1. So 2 itself and 1 is a factor of all. So 1 is a common factor of all the numbers. 2 is itself. Like this type of numbers we can call it as prime numbers. So now here, what is irrational number? Roots of prime numbers. Here prime numbers are 2, 3, 5, 7, 11, 13, so on. These all are prime numbers. If we include root 2 prime numbers, if we include root 2 prime numbers, root 2, root 3, root 5, root 7, so on. These all are irrational numbers. These all are irrational numbers. Why these all are irrational numbers? These all are non-terminating decimal. These all are non-terminating. In non-terminating, non-recurring also. So non-terminating, non-recurring decimals are irrational numbers. Last class we have discussed. So now coming to real numbers. Real numbers means real numbers. Now the combination of rational numbers and irrational numbers is called real numbers. The combination of rational numbers and irrational number we can call it as real numbers. Rational numbers represented by q and irrational number represented by q dash or s. Q dash or s. So now real numbers represented by capital R. So R is equal to rational number union irrational number. This union indicates combination. So the combination of rational number and irrational number is real numbers. Okay. So in our 10th class, first chapter is real numbers. In this real number, the real numbers are the first person who is discovered real numbers. The first person defined real number is, the person name is Richard Dedekind. Richard Dedekind. He is the first person to introduce real numbers. In this real numbers, the first topic is Euclid's Division lemma. Euclid's Division lemma. In shortcut, we can call it as EDL. EDL. Sometimes we can call it as Euclid's Division algorithm also. Euclid's Division algorithm, that is EDA. So, what is Euclid's Division lemma or what is Euclid's algorithm? Let us discuss with example. Say here, if 20 is divided with 5. If 20 is divided with 5, 5 fours are 20, The remainder is 0. The remainder is 0. In previous classes, we have learned about this division parts. So, what are the names of this division? Means 20, we can call it as dividend. 20, we can call it as dividend. This is called it as dividend. 5, we can call it as divisor. 5, we can call it as divisor. 4, we can call it as quotient. 4, we can call it as quotient. 0, we can call it as remainder. This is called it as remainder. So according to division algorithm, how we can write the formation, how we can write the equation? Tell me now. Now dividend is equal to divisor into quotient plus remainder. Dividend is equal to divisor into quotient plus remainder. Now let us check. Here 20 is dividend. So here 20 is equal to 5 into 4 plus 0. 5 into 4 plus 0. So dividend is equal to divisor into quotient plus remainder. Once we check this process is correct or not. See here 20, 5 4s are 20 plus 0, 20. Okay, now let us check with another example. If 21 is divided with 5, if 21 is divided with 5, 5 4s are 20, the remainder is 1. 5 4s are 20, the remainder is 1. We should write a division algorithm. Here dividend is equal to divisor into quotient plus remainder. So 21 is equal to 5 into 4 plus 1. 5 into 4 plus 1. Now 5 4s are 20. 20 plus 1, 21. So 21 is equal to 5 into 4 plus 1. This is the division algorithm. Like that, by using Euclid's division lemma. So here what is Euclid's division lemma? See, let for any positive integer a comma b, for any positive integer a comma b, there exists unique pair of integers q comma r satisfying the condition a is equal to bq plus r. A is equal to bq plus r, where r is greater than or equal to 0, where r is greater than or equal to 0, less than b. So what is, once again I will repeat. See here, what is Euclid's division lemma? For any positive integers a comma b, there exists unique pair of integers q comma r satisfying the condition a is equal to bq plus r. A is equal to bq plus r, where 0 less than or equal to r less than b. It means the remainder should be greater than or equal to 0 and less than b. So here what is a, what is b, what is q, what is r? Just now we have discussed division rule, division algorithm. Like that, see here a is, we can call it as dividend. A is, we can call it as dividend. B we can call it as divisor. B we can call it as divisor, and 4 we can call it as quotient. Here 1 is remainder. So in this case, in this problem, what is the value of a here? A is equal to 21. And b is equal to 5 and q is equal to 4, and the remainder should be 1. So here 21 is equal to 5 into 4 plus 1. Now what about this 0 less than or equal to or less than b? So the remainder should be, in Euclid's division algorithm, the remainder should be always lies between 0 to the value of b. B in the sense what? Divisor. So the remainder is always between 0 to divisor. Now once you check it, in this problem now what is the remainder here? 1. So this remainder is always less than the value of divisor. So 1 less than 5. So the remainder, just you remember that this remainder is always less than the divisor. Less than the divisor. Okay, less than the divisor. Now, what is the use of Euclid's division lemma or Euclid's division algorithm? So, by using Euclid's division lemma, we have to find the HCF of 2 or more numbers. We have to find the HCF of 2 or more numbers. So, once we check it, see, find the HCF of 96 and 72. 96 and 72. Just now I said here what is the uses of Euclid's division lemma. By using EDL, by using Euclid's division lemma, we have to find the HCF of 2 numbers or 3 numbers, 2 or more numbers. Let us check with example 96 and 72. So 96, when we can take a big value, greater value. What is the greater value? Here 96. Greater value is divided with the smallest value. Okay now. So 96 divided with 72. Now 72 ones are 72. Here remainder is 24. The remainder is 24. Again we can take divisor. Here while we are doing the next division, while we are doing the next step, this divisor becomes dividend. Divisor becomes dividend. So 24 3s are 72. So the remainder is 0. So this process is we should continue until the remainder we get the remainder is 0. This process is we are going to continue until the remainder we get the remainder is 0. Now we got the remainder is 0. So once again repeat here 96 divide with 72. 72 ones are 72. Here remainder is 24. This remainder is 24. Afterwards this divisor becomes dividend. So 24 3s are 72. The remainder is 0. Now in this case by using Euclid's division algorithm, what is the condition of Euclid's division lemma? A is equal to BQ plus R. A is equal to BQ plus R. We should write 96. In first case, what is the dividend? 96. So 96 is equal to 72 into 1 plus 24. 96 equal to 72 into 1 plus 24. Now next case, this 96, this 72 into 1 plus 24. Again this 72, this divisor is becomes dividend. Divisor is becomes dividend. So 72 equal to 24 into 3 plus 0. 24 into 3 plus 0. So it is in the form of A is equal to BQ plus R. Now once check this condition also. So just now I said the remainder is always less than the B. Less than the B means divisor. Once you check it, this here in first case, what is the remainder? 24. This 24 is less than the 72. In next case, what is the remainder? 0. This 0 is less than the 24. Less than the 24. So by using Euclid's division lemma, we have to find the HCF of 2 numbers. Let us see one more example. $900 and 270. So already I explained. First we can take the greatest number, divide with the smallest number. 900 divide 270. So 270, how much are 900? Once you check it here, 270 4s are 270, 3s are 3 zeros are 0, 3 7s are 21, 2 3 2s are 6 and 8 1 0. So 273s are 810. 273s are 810. Again the remainder is here 90. The next step is this divisor becomes dividend. So B becomes A. Now here in first case this is the value. What is 270? This is the value of B. This is the value of A. This is the value of Q. This is the value of R. Okay. Now it becomes, this 270 becomes A. This 270 becomes A. Next the remainder becomes B. This remainder becomes B. 93 is 270. The remainder is 0. Okay now. So according to the ideal condition, according to the condition A is equal to BQ plus R. Now here 900 is equal to what? 270 into 3 plus 90 plus 90. In next case 270 is equal to 90 into 3 plus 0. 90 into 3 plus 0. Okay. Now this is Euclid's division lemma. So by using Euclid's division algorithm, we have several applications related to finding properties of numbers. Now how those are found we can see. Okay, for example, so by using Euclid's division algorithm, several applications related to finding properties of numbers. So in this, the first one is show that any positive odd integer of the form 6q plus 1 comma 6q plus 3 comma 6q plus 5 6q plus 5. So here any positive integer, show that any positive odd integer of the form 6q plus 1, 6q plus 3, 6q plus 5. So now by using Euclid's division lemma, we have to prove that any positive odd integer of the form 6q plus 1, 6q plus 3 and 6q plus 5. Let us see A be the any positive integer here. Let A be the any positive integers. Just now already in EDL we have discussed A comma B. For A comma B, any positive integers and there exists unique pair of integer q comma r satisfying the condition A is equal to BQ plus R. Now we can take here, let A be the any positive integer and B is equal to 6. And B is equal to 6. Here why we are taking B is equal to 6? According to this 3, here 6q plus 1, 6q plus 3 and 6q plus 5, it is in the form of BQ plus R. Once you compare BQ plus R, here what is the value of B? So B is equal to 6. According to this condition, we have to take the value of B. So B is equal to 6 and Q is quotient here. What is Q? Q is quotient. Now by using Euclid's division lemma, what is the Euclid's division lemma condition? A is equal to BQ plus R. Where R is always greater than or equal to 0 and less than B. So here according to this condition, 0 less than or equal to R less than, here we know the value of B 6. So here the remainder should be from 0 to less than 6. So the possible remainders are see, R is equal to 0, 1, 2, 3, 4, 5. Why we are taking 0 to 5 here? So according to this limits, 0 less than or equal to or less than B. So the remainder should be greater than or equal to 0 and less than the value of b. So the remainders are from 0 to 5. 0 to 5. Less than 6 means 5. So 0, 1, 2, 3, 4, 5. So in this case, if r is equal to 0, if r is equal to 0, then a is equal to what? A is equal to bq plus r. Here b value 6q plus the remainder is 0. So that is equal to 6q. That is equal to 6q. So here if r is equal to 0, that implies a is equal to 6q plus 0 is equal to 6q. 6q we can write 2 into 3q. 2 into 3q. When the multiple of 2, it is a even number. 2 into 3q means what? It is a even integer. So this is a even. So in this case, this is not a odd. So this is not satisfied. Next, coming to r equal to 1. If r equal to 1, then a is equal to 6q plus 1. In the place of r, we substitute 1. So 6q plus 1 means we can take 2 into 3q plus 1. 2 into 3q plus 1. Here 2 into 3q even number. Even plus 1 means odd integers. So this is a odd integer. Now coming to r equal to 2. If r equal to 2, that implies a is equal to 6q plus 2. 6q plus 2. In this 2 taking common. Here 2 taking common, 2 into 3q, and if 2 is taking common here 1. Once again you check it. 2 into 3q 6q plus 2 into 1 2. So this total 3q plus 1 is product. It is a multiple of 2. It is a multiple of 2. So 2 into 3q plus 1 is even number. In this case also we don't want even. So next, if r is equal to 3. If r is equal to 3, then a is equal to 6q plus 3, that is equal to 2 into 3q plus 1 plus 1. 2 into 3q plus 1 plus 1. How? 2 into 3q 6q plus 2 into 1 2 and plus 1 3. So this is a even or odd? This is total even. Even plus 1 is equal to odd. This is a odd. And one more, if r is equal to 4, if r is equal to 4, that implies a is equal to 6q plus 4, that is equal to 2 taking common here 3q plus 2. 3q plus 2. 2 into 3q 6q and 2 2s are 4. So now this is a even number. Why even number? This is a 2 multiple. So this is a even number. This is a even number. Next, the last case, if r equal to 5. If r equal to 5, that implies a is equal to 6q plus 5. 6q plus 5, we can write 2 into 3q. 3q plus 2 plus 1. This is the odd integer. This is the odd integer. Now see, 2 into 3q 6q plus 2 2s are 4 and plus 1, that is 5, odd integer. So what is the question here? Show that any positive odd integer of the form 6q plus 1, 6q plus 3 and 6q plus 5. So according to Euclid's Division lemma, according to this condition, we have shown here 6q plus 1, 6q plus 3 and 6q plus 5 are odd integer. Okay, in this EDL, the second case problem, show that the square of any positive integer of the form. Show that any positive integer (3p, 3p plus 1). 3p, 3p plus 1. In second case, show that square of any positive integers. Here in first case normal. Show that show that any positive integer, any positive odd integer of the form. That is in first case. Coming to second case, show that square of any positive integer of the form 3p comma 3p plus 1. 3p comma 3p plus 1. See, as the same, let a be the any positive integer. Let a be the any positive integer. Let a be the any positive integer and b is equal to, what is b? According to the condition, what is ideal condition? A is equal to bq plus r. A is equal to bq plus r. So these numbers comparing with this condition, a is equal to bq plus r. Bq plus r. B. Then what is the value of b here? 3. So b is equal to 3 and q is quotient. Q is quotient. Next, by using Euclid's division lemma, now what is Euclid's division lemma condition? A is equal to bq plus r. A is equal to bq plus r, where 0 less than or equal to or less than b. It means the remainder should be greater than or equal to 0 and less than b. So here 0 less than or equal to or less than, the value of b is 3. So the remainders, what are the possible remainders here? 0, 1, 2. Less than 3 means up to 2. So the possible remainders are, the possible remainders implies r is equal to 0, 1, 2. 0, 1, 2. Now, in first case, if r is equal to 0, if r is equal to 0, next same condition, a is equal to bq plus r. So now a is equal to, the value of b is 3 and q plus r, the r value is 0. So here a is equal to what? 3q. That implies a is equal to 3q. A is equal to 3q. In first case, directly we got odd integer or even integer. But in this case, we have to do squaring on both sides. Why? Because here given, show that square of any positive integer, of the form. So we have to do squaring on both sides. SBS, squaring on both sides. Now a square is equal to 3q whole square. Now a square is equal to, here what? 3 square value 9 and q square. So 9q square we can write 3 into 3q square. 3 into 3q square. So this is equal to 3p, where p is equal to 3q square. So see, a square is equal to 3q whole square. Now a square is equal to 9q square, then 3 of 3q square. Why we can convert it into 3 of? Here given, show that of the form 3p and 3p plus 1. So we are taking common 3 and the remaining is 3q square. So in the place of 3q square we can take p, where p is equal to 3q square. Next in the second case, if r equal to 1, then a is equal to 3q plus 1. A is equal to bq plus r. So a is equal to what? B value 3, q plus r value is 1. Now squaring on both sides. Now a square is equal to 3q plus 1 whole square. Then a square is equal to a plus b whole square. It is in the form of a plus b whole square. Now 3q square a square plus 2ab. 2 into 3q into 1. A square plus 2ab plus b square. Now a square is equal to 9q square. A square is equal to 9q square plus 2 3s are 6q into 1q. So 6q plus 1. 6q plus 1. So now a square is equal to, we are taking common 3. Why we are taking common 3? We have to show in the form of 3p and 3p plus 1. 3p completed here. Now we are going to show 3p plus 1. So here we are taking common 3q. We are taking common 3 common. The remaining term is 3q square plus 2q plus 1 outside. We have to write plus 1 outside. Now once again you check it. 3 3s are 9, q square plus 3 2s are 6 and q plus 1. Now we can take a square is equal to, this complete value is equal to p plus 1, where p is equal to what? Where p is equal to 3q square plus 2q. Okay, so this is a square is equal to 3p plus 1. Like that we have to show square of any positive integer of the form 3p and 3p plus 1. 3p and 3p plus 1. Next, coming to third case. Show that cube of any positive integer. Okay, cube of any positive integer of the form 9m plus 1 and 9m plus 8. So we have to, here we did squaring on both sides. In that case we have to do cubing on both sides. Cubing on both sides. See, show that in third case. Okay, so third case what? Cube. Show that cube of any positive integer of the form 9m comma 9m plus 1 comma 9m plus 8. 9m comma 9m plus 1 comma 9m plus 8. Let us see here. Same, first step what? Let a be the any positive integer. Let a be the any positive integer. Any positive integer and b is equal to, and b is equal to, then what is the value of b here? Same, a is equal to bq plus r, bq plus r, then what is the value of b? 9. The value of b is equal to 9, and q is what? Q is quotient. Q is always quotient. Now next, by using Euclid's Division lemma, by using EDL. Now what is the condition of EDL here? A is equal to BQ plus R. Just you remember that Euclid's Division lemma. What is the condition of EDL? A is equal to BQ plus R, where the R is greater than or equal to 0 and less than B. So now 0 less than or equal to, here remainder is less than B value, the value of B. B means what here? Divisor. So B is equal to what? 9. So according to this condition, the possible remainders are starts from 0 and end to less than B value. Here B value is 9. So the remainders are up to 8. 0 to 8. So the possible remainders implies R is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. Now first case, if R is equal to 0. If R is equal to 0, tell me, if R is equal to 0, then A is equal to, what is the value of B here? The value of B is 9 and Q plus the remainder is 0. The remainder is 0. So that implies A is equal to 9Q. A is equal to 9 cube. What is the next step? In first case, directly. Okay now. So in second case, we are squaring on both sides. In third case, here show that cube of any positive integer of the form given. So we have to do cubing on both sides. Cubing on both sides. So here cubing on both sides. Cubing on both sides. So now a cube equal to 9q whole cube. 9q whole cube. So a cube is equal to here 9 cube we can write 9 into 9 square and cube. 9 into 9 square. 9 square into 9, 9 cube, right? Into cube. So a cube is equal to 9 of 9 square value 81 cube. Understand? See here 9q whole cube. So here 9 3 times. So 9 and 9 square. Here 3 times, no? Now cube. So 9 taking common. Here 9 square means 81 and cube. So a cube is equal to 9. In the place of 81 cube we can write m. We can write m. Why? Because we have to show the form 9m. So where m is equal to 81 cube. 81 cube. Next, coming to second case. What is second case? If r equal to 1. If r equal to 1. That implies a is equal to same 9q plus 1. 9q plus 1. Next, cubing on both sides. Cubing on both sides. Tell me, cubing on both sides. See, a cube equal to 9q plus 1 whole cube. 9q plus 1 whole cube. Now see, a cube equal to, it is in the form of a plus b whole cube. What is the formula of a plus b whole cube? A cube plus 3a square b plus 3ab square plus b cube. So now here where a is equal to 9q and b is equal to 1. So 9q whole cube a cube plus 3a square b 3 9q whole square into 1 plus 3ab square 3 into 9q into 1 whole square plus b cube 1 cube. Here write a plus b whole cube equal to a cube plus 3a square b plus 3ab square plus b cube. This is very important. A plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. So here a, where a is equal to 9q and b is equal to 1. Here a cube plus 3a square b plus 3ab square plus b cube. Now let us see 9q cube. Here 9q cube we can write 9 into 9 square cube. Okay, 9q whole cube we can write 9 into 9 square cube. Here 9 square and 9 cube. Here cube plus 3 into 9 into q square. 3 into here 2 9s. So 9 into q square plus here 3 into 9 into q. 3 into 9 into q plus 1. So in these three terms, we can take the common 9. We can take the common 9. If you are taking 9 common in first term, the remaining terms are 9 square and q cube. 9 square and q cube. 9 square value 81 and q cube. Coming to second term. If you are taking 9 common, 1 9 is taking common, the remaining terms are 3 9 q square. 3 9s are 27 and q square 27 q square plus. Next, here 9 taking common, here also in third term 9 taking common, the remaining term is 3q. The remaining term is 3q plus 1 we can write outside. We can write outside. Now this value, this total value, we can write m. This is m. This is plus 1. 9m plus 1. Here what is the value of m? Where m equal to 81q cube plus 27q square plus 3q plus 3q. Now we have shown here cube of positive integer 9m and 9m plus 1. The next one is what? 9m plus 8. Now we can take r is equal to 2. See, okay, in third case, if r equal to 2, if r equal to 2, that implies a is equal to 9q plus 2, 9q plus 2. According to Euclid's Division lemma condition, a is equal to bq plus r. Here 0, here 1 in second case, in third case 2. Next step what? Cubing on both sides. Cubing on both sides. Cubing on both sides. Now a cube equal to 9q plus 2 whole cube. 9q plus 2 whole cube. Same LHS a cube equal to, it is in the form of a plus b whole cube. Already I have written here a plus b whole cube formula. A cube plus 3a square b plus 3ab square plus b cube. Here where a is equal to 9q and b is equal to 2. So write down here 9q whole cube. A cube plus 3a square means 9q square b 2 plus 3ab square. 3 into the a value is 9q and b value is 2 square plus b cube means 2 cube. Means 2 cube. See here. Okay, see a cube plus 3a square b plus 3ab square plus b cube. Now split here. Here 9q cube. We can write 9 into q cube. Observe carefully here. Plus 3 into 9q whole square. So 3 into 9 square means we can write 9 into 9. 9 into 9 and q square and 2. And 2. Next here 3 into 9q into 2 square value 4 plus 2 cube is 8. 2 into 2 into 2. 3 times of 2 is equal to 8. Now we can take the common 9. Why? Because we are going to show the form of 9m plus 8. So in these 3 terms we can take the common 9. In first term we can take common 9, the remaining is q cube plus, and see here 9q whole cube means here 9 cube q cube, 9 cube q cube. Here if you are taking common 9, the remaining term is 9 square q cube. The 9 square value 81 q cube. The 9 square value is 81 q cube plus here 9 taking common the remaining terms 9 and 3. 9 3s are 27, 27 2s are 54 q square. 54 q square. Once again see here 3, here 9 square means 2 9s and q square and 2. 1 9 is taking common, 3 9s are 27, 27 2s are 54 q square plus in third term 9 taking common. The remaining terms 3 and 4 and q. 3 4s are 12 and q 12q. 12q and plus 8 right outside of the brackets. Now this is 9. This total value is equal to m plus 8. So where m is equal to 81 q cube plus 54 q square plus 12q plus 12q. Now so like that we have shown the cube of positive integer of the form here 9m, and in second case 9m plus 1, in third case 9m plus 8. Okay,